Hi there, welcome to my video. I can move this down a little. So today I actually have tea. It's cold. It was warm probably an hour ago, but anyway, it's still there. Let's see. So today, I think I want to think some more about the concept of work. So let's say work equals force times distance. Actually, let's take it a step back. Let's play with forces. I think I'll do that. So force equals mass times acceleration. If you're talking about a I don't know how to say it. I guess a force that's acting on mass, maybe. Or if you're talking about an electric force, force equals the electric field times Q. And all these with the little arrows are vectors. Mass is a scalar and charge is a scalar. So, well, let's work with this one for a minute. So let's say that we have so in the very beginning stages, someone would see this as F equals ma. So let's say that we have this object and it's a ball and it's sitting above the ground. Well, not sitting, it's the moment it's hovering above the ground. And let's say magically it's about to be released. If you wanted, you could say there's a string on the ball, and then maybe the string gets cut and the ball starts to fall. So we could say, what's the force on the ball? Well, we would say, what's the mass of the ball? And typically this is in kilograms. If you're using the SI units, which are easier to work with in physics. So let's say this ball was 2 kilograms. And in this case, acceleration would be g, because it's Earth is what's the force that's causing this to move down. So there's a force moving downwards. There's also an acceleration moving downwards. So maybe this pink arrow represents the vector, the direction. It should also equal the magnitude, but I don't know yet. Well, force is going to be bigger, so let's say, and technically they're both acting on the ball. So I'll draw them acting on the ball. Right, so let's erase those. So on this ball acting straight down, there's an acceleration vector, and maybe it's like that. And there will also be a force vector, which is going to be a bigger value. And yeah, so the acceleration here is g, because it's the force that's doing the acting, the force that's causing the acceleration here, or the acceleration that's causing the force, whichever way is more appropriate. The Earth, the gravity of the Earth is what's doing the moving of the object. It's what's causing the force on the object. So in this case, g standing for a constant that represents the acceleration of an object close to the surface of the Earth, meaning like not in outer space, basically, is going to be 9.8 meters per second squared. So force in this case then is just going to be force equals 2 kilograms times 9.8 meters per second squared. And if I allow a little bit of rounding here, this is going to be approximately 20 kilograms times meters over second squared, which is the same as 20 newtons. Kilograms times meters over second squared is equivalent to newtons. So in this case, we see that force equals mass times acceleration. Now, we don't have to think of the relation. So you can think of this as a formula, but I prefer to think of it as a relationship because I don't know, for me, maybe it's just me, but when I think of the word formula, I think you plug in these things and you get this result. When I think of relationship, I think that I know the ratios of the different quantities and how they relate to one another. And I think that's more helpful. So if you were trying to learn this, you would want to ask yourself, well, like let's take this problem and you have a ball that's about to fall. And you might say to yourself, okay, well, what's going on here? You have the mass of the ball, you have a force causing the ball to move towards the earth, you have an acceleration of the ball towards the earth, and you also have some other things that we didn't mention. Let's use blue here. You have velocity, which, off the top of my head, I don't know if velocity will be bigger than acceleration or not, but we'll just draw like that. So you have velocity, which is also a vector, and velocity is not just technically a vector, velocity changes over time. So you have a velocity value here, which let's do, I'll draw this as a dot. So this is the initial first velocity value. It's 0 because it's not moving. Then once you cut the string was preventing the force from causing motion. Once you cut the string, then nothing is preventing the, well, not nothing, but nothing significant at the moment is preventing the ball from moving. So you have acceleration, and as you have acceleration, you have changing velocity, and over time, the velocity continues to grow. So at each little time here, you would see that the velocity would grow until, bam, it hits the ground, which I think actually it would look more like it would hit the ground right there. So all the way until it hits the ground. So in this case, this would be velocity initial. This would be velocity final. We have some other things going on in this picture that are worth mentioning at the moment. I'll just continue as blue for a minute, I guess. So let's see. You have positions. So the first position here, you can label this, different things. It's often labeled different things. If you were to lay out a XY axis like this, so that this is X and this is Y, then this position up at the top would be Y max. You could have also made this Y min and the ground Y max. I just happened to make, when I laid out my axes, I put the positive axis on y-axis at the top. You could have also put the negative y-axis at the top. It's just a matter of preference. and we call this down here y min. And now that I've labeled my axes, technically I would have to go in and change these values. So now, technically this here would be a negative 20, because force is a vector, and it is moving in the negative direction on the y-axis. So it would be negative 20. Because of that, so I don't have to go change my numbers there. And you would get the negative value by making g negative, because g points towards the ground. So g would be negative. But if I want g to be positive and I want the force to be positive, then I'm going to have to switch this max and min. And switch where the positive value is. So this will be min. So this would probably be 0. This would be max. And this would be the positive y direction. So, and I think that's pretty much it. Yeah, so relevant relevant equations here. I'll start to use yellow. We have force equals mass times acceleration. So that's just a relationship between these three values. So if we wanted to write it this way, we have, let's say, relationships. A lot of times, I think would be easier to solve problems if you think of these as relationships instead of just formulas, because you may want to solve this for acceleration, you may want to solve this for mass, you may want to solve this for force, and if you just had one formula that you were working with, you could just easily change it every time. But what happens often is you have to flip through a bunch of different formulas, so I think it becomes perhaps easier to think of them as relationships. So first of all, we have a relationship that relates force, mass, and acceleration. And these are, you would say, I might mess up the words a little bit, but I believe you would say force is proportional to mass and acceleration. Maybe that's how you would say that. I kind of mix up those relationship words some. Let's see what else. But then you also need to know constraints. So there's some constraints on this. It's not necessarily true to say that F equals ma. It depends on context. In this context, it's true to say that F equals ma because the force and acceleration are both headed in the exact same direction, and because the force, the mass, and the acceleration are constant over the interval. They're not changing values. The velocity changes over the interval, but the force, mass, and acceleration do not. And because they do not change, you can set them up as such. So let's say if we say no changing, I guess, no changing. Oops. Then you would have force equals mass times acceleration. So that should also be and same direction. Okay, well, that's not fully legible, but all right, so let's say now, what if one of these things isn't true? Let's see how I can do this. Yeah, okay, so let's say we have this I don't know which way I'm going to want to draw this, but so let's say we have this ramp here. Let's say this is a right angle. This is some angle theta. This now is our height. So I'll say h, but we could also say, if I want to keep the axes the same, we could say that this is y min, this is y max. Oops, let's make that subscript. Y max. And so now our axes are like this, and I'm going to leave the positive side of x here and the positive end of y down here. So like that. And now, let's say that we start off with a ball, kind of the same, sitting on this incline, and there's a string, it's attached to something. And let's say we cut this string. Well, what's going to happen to the ball? Let's use this color. So when we cut that string, the ball's going to roll. It's not going to roll straight down because it can't, because this incline that it's sitting on is preventing it from doing so. So it will roll this way. Now, yeah, so it rolls this way. Think for a second. Since it moves in this direction, the velocity is in this direction. So this is not going to be a vector to scale anymore. This is just going to be to show the direction. The velocity moves in this direction, and the acceleration moves in this direction. But the force is acting in this direction because it's the force of gravity that is pointing on the Earth. And technically there's also a friction force, which I'm going to just ignore for right now. And because this is a circle rolling, I'm not actually sure which direction the friction points. I think it points this way. I believe so. I know sometimes with a wheel it points in the same direction, but I think that's when the wheel is propelled. So anyway, if we were considering friction, it would be in this direction, I believe. I'm like 90% sure. But we're gonna ignore that for right now. So we'll just kind of hide that. All right, so now we can take and we can redraw this in what's called a free body diagram, and we can say that we have we can just look at one or the other. So let's say we want to look at the forces. Normally you would only do this for the forces, but I suppose we can also do it for the other things. It won't be very relevant, but we can do it. So we have force. We have a force acting in this direction, and oh yes, okay, we do have another force that I missed. We have the normal force of the ramp. So let's say this is force normal. This is the force of gravity. Now, the normal force is just meaning the force that's perpendicular to the surface, and it represents whatever chemical bonds or whatever is going on inside that object to keep the ball from just pushing through the object, so that the object is acting like a solid object. And technically, I guess the force would be between the two objects pushing against one another, the force of the ball here and the force of the say the board of the top of the plane. So that's going to point roughly in this direction. It's going to be at a 90-degree angle to the surface of the plane. And right, so this represents the forces in general. So this is the normal force, and this is the force of gravity. And then we also have the force of friction, except I'm going to ignore that. So, frictionless surface, yada yada. We can imagine it's completely frictionless, some type of super material that's more slippery than ice. The ball and the plane, both. So anyway, so then to find the force, how did you say this? The force of motion, I guess. I'm not sure what this would usually be labeled. You need to add these vectors together. And if you do your little parallelogram method here, you can kind of get a pretty good sense. Oops. That the force will move in this direction, because this is the sum of these two vectors. So we'll say force m from force, the motion of the force, whatever. Or actually it should be like force net, the net force. Alright, so that's the net force. And you could also take, so let's say this is the ball again. We have a velocity vector. The velocity vector will be in the same direction as the net force. We also have an acceleration vector. The acceleration vector will be in the same direction as the net force. And then we have position vectors, but the way I set this up, I set my XY axis up like this. Actually, I have another video that I already made how it's usually easier to make your XY axis parallel to the plane. So to call this X and to call this Y. Let's see if I can just keep it the way that I did and not make any mistakes when I try to solve it. Alright, so we have this setup. So then what you would need to do, there's a couple of ways to do this. So in this case, the relationship is no longer F equals m times a, or force equals mass times acceleration, because here the force, that it depends on which force you mean. Okay, so the force of gravity is equal to F equals m times a. The normal force should be equal to basically the component of gravity that would be 90 degrees to this incline. So like, let's take my XY axis here in red. The normal force will be equal and opposite to the force of gravity, except only the portion of the force of gravity that would be equal and opposite to this direction, if that makes sense. And what else? Yeah, and then we have the net force. So, which is going to be equal to the sum of these two forces, the force of gravity and the net force. So there's different ways that you could do this, but basically you can say that the net force equals the force of gravity plus the normal force. And then normally the way that I would do this, I'm trying to think, I think you could do it a little different if but the way that I would like to do this, the way that I would normally do this, is to break everything down into their component parts. So the force, oops, I don't need a, so that's no longer a vector value. The force in the y direction equals the force of gravity in the y direction, which is negative according to the way I set up, no, which is positive. The force of gravity is moving in the positive y direction. So that one's positive, minus the normal force. And it's minus because the normal force, as you can see from the diagram here, it's moving in the negative y direction. All of it, some of it's moving in the negative x direction, and some of it's moving in the negative y direction. None of it is moving in the positive y direction. So this is going to end up being minus. Then we have the force of x, force in the x, the net force in the x direction equals the force of gravity in the x direction. And now, once again, our normal force has some of it going in the negative x direction, none of it in the positive. So this is going to be negative. It's normal. And I didn't actually assign any values. So let's say that you knew the mass of the ball, just like over here. Let's say that the only thing that we know is the mass of the ball, which we'll call m. So we have the force of gravity, that is 100% in the positive y direction. So the force of gravity would be just F equals m times a, and m times a is the same here as mg, because the acceleration is g. Force y. Now the normal force, this is the part that I always mess up when I don't rotate the axes. So let's see. I don't have a lot of room. It's right over here. So what we have right now is this, and we have a force moving downward, and we have a force in this direction, and now we want to break this into components. So we have this angle right here, which if we draw, so okay, these two lines represent the forces. If we draw another line that represents the plane goes like this, and we have this angle here is theta, which means that if this angle is theta, this angle is theta, assuming that this dashed line is parallel to the x-axis here, which it is. So this is theta, this is theta, this is theta, and this is 90 degrees to theta by definition. So this angle, what's the other angle? This angle here then is theta. Because this is theta, theta plus 90, so then this must be theta, because, or how to say this? So 180, so 180 minus, no, equals 90 plus x, or how about let's pick a new variable, plus d, that's just a random letter, plus theta. So 90 equals d plus theta. Let's see, are these really the same? So Yes, this is theta. So actually, no. Theta is 90 minus d. So this should be a d. This angle should be a d. So I'll call that phi. I hope that's not too confusing. Let's call this phi, because that's normally another name for angles. Alright, so now we're dealing with angle phi, which equals 90 minus theta. So if you were given a theta, you'd have to say phi equals 90 minus theta. Alternatively to all this, it would have been easier just to rotate the axes in the first place, but alas, I didn't do that. So, I made a real mess of that, so let's go back to this and turn it into a triangle here. Alright, so this is phi, and this is the normal force in the y direction, and this is the normal force, meaning the total amount, and this is the normal force in the x direction. So we can say that if you have your trig identities memorized, you would see that sine equals opposite over hypotenuse. So sine of phi equals the y divided by the total. So the total times sine of phi equals the y. So the force normal the y direction equals force normal times sine of phi. And you could go through it and figure out that the force normal in the x direction equals the force normal, the magnitude, times cosine of phi. So now, plugging these in, the force normal is supposed to have a y here. Force normal y, and this is supposed to have an x here. And this force of gravity in the x direction is 0. You can see it's always 0 because the force of gravity always points, none of it shifts to the left or to the right. All of the force from gravity is acting straight downwards towards the center of the earth, which for our purposes here is straight down. So the force in the y direction equals mg minus the magnitude of the normal force times sine of phi, and the force in the net force in the x direction equals negative normal force, sorry, in the x direction, which is negative the magnitude of the normal force times cosine of phi. And yeah, so when you add these two together, so to get the force normal net is actually equal to the sum of the two vectors. So to find that, you're going to add the components. You're going to square each component, and then you're going to take the square root. This is a square root sign. Alright, so the y component, mg minus fn sine of phi squared plus, and this is actually the magnitude of the net force, plus negative magnitude of the normal force cosine of phi squared, square root of the whole thing. So this is the magnitude, And I could change this phi to have it 90 minus theta, since I'm assuming we're given theta initially and not phi, but anyway, you get the idea. So in some sense, let me erase some of this. And then this is just the magnitude. To calculate the direction, you're going to have to calculate, well, whatever direction you want to, whatever you want your reference point to be. So if you wanted your reference point to be the axis that I set up, you would have to say that it's going to be this angle down to here, where this represents the plane. So whatever the angle is from this horizontal down to this plane, that angle would be the direction. Yeah, so let's bring this back to the initial stuff that I brought up. So in some sense, force equals mass times acceleration. And this is a relationship between force, mass, and acceleration. But this only holds true when they all point, the two things that are vectors, the force and the acceleration, both point in the exact same direction. If they do not, so also, okay, so sort of I got off track a little bit because this was dealing with multiple forces. I should have kept an example that just had one force. But if we have multiple forces, then in this case, we see that the magnitude of the net force equals the square root of mg. Well, and if I were to keep g, so this is also the same as mg. So F equals mg. But the net force, when you have multiple forces, which you would have for an object rolling downwards, it's going to be mg minus the magnitude of the normal force times sine of phi squared plus negative normal force cosine of phi squared. All that under the square root sign. Technically, it should keep going like that. Hopefully that's not too messy. Yeah, so this then represents the force. And we're mostly still using the same values, so we're still given mass, we're still given g for acceleration. And then other than that, we just basically have some angles, and we have to consider a force working against our force that we're dealing with now. You also have, alright, so let's try to set up a new example. This one's going to be really hypothetical because the reason that I ended up skipping over it is because I actually can't think of I don't have an example in mind that would represent some kind of reality. I'm sure there is one, I just don't have it in mind. So let's keep that one. Alright, so one more thing here. Let's use pink. Alright, so let's take the acceleration, the force, the mass. So we want to relate force, mass, and acceleration. And how could you do this? Let's say that we were going through, this is going to be a little bit contrived. Let's say that we want to take this ball and it's on a string that's like tied up to something. And we're going to drop it But when we do, let's say that it drops through some kind of like a gummy kind of fluid, so that it can still slide through it, but it gets slowed down. Okay, I don't know, use your imagination what that could be, but and let's say it even does it multiple times. So in this case now, and let's say the ground, well, yeah, let's not worry about that. So let's say that we cut the string here, and our object starts to fall. So it's gonna feel a force that moves in this direction, and this is the force of gravity. This actually isn't quite gonna work either. I almost think you'd have to imagine a hypothetical world where as the force flows, as the object moves through positions in space, let's say that these little donut looking things that I drew, these little plates or whatever, these little like cylinders, that they represent places where for some strange reason the acceleration is different here. So let's say that here the acceleration does not equal g. Let's say that here the acceleration does not equal g. I'm not sure that that's possible. I was first imagining it going through a fluid, which is kind of almost going to end up being similar, but technically, I mean, I guess the acceleration wouldn't equal g. I guess it's okay to say that. I'm going to say that. So as it falls, when it gets to, this point right here, where it's sinking through this pink stuff, it's going to slow down a little bit. Then it's going to pop back out and start to move fast again. And then it's going to hit this and slow down a little bit. And then it's going to come down here and it will pop out again. So in this case, the force changes because the acceleration changes. Oh, actually, I did just think of a more realistic example. I don't technically know how to solve it, but the example of a rocket going up where the mass changes. But in this case, let's say, so we have force, we have mass, and we have acceleration. Let's say that mass is constant. But let's say that for the way that I set this up, I kind of mixed two things. So on the one hand, I assumed that we knew the force because I kept saying that the force was changing. But on the other hand, I assumed that we knew the acceleration because I wrote out the acceleration change. So let's just pick one. Let's say that the acceleration changes and we don't know what happens to the force. Just, hypothetically. For the sake of trying to solve the problem. We do know what happens, but let's just ignore it for a minute because we don't want to. I don't think we want to think about the force just yet. So if we have mass and we have acceleration, and the mass is constant, but the acceleration changes, then it's not true to just say that the force equals the mass times the acceleration. And the reason is because over the time, over the event, let's say, that this object travels from our starting point down to our finishing point, what value do we choose for acceleration? If we choose the max starting value, which is g, at this position up here at the top, acceleration equals g, then if we solve this, force equals mass times acceleration, and we say that F equals mg, then our solution will be as if there was nothing slowing it down. The easiest way, obviously, in this case, maybe the only way, I don't know, would be to say that to break this up. So in the first portion we have force equals mg. Then here we have all I technically know from what was given is that force is less than mg because I said that it slows down. So we know that the acceleration is less than g. I don't know how much less, but here we're going to have f is less than mg. Then here we're going to have f equals mg. And then here we're going to have f is less than mg. And here we're going to have f equals mg. So to find the total force, I don't know if that's technically correct in this case because this isn't a total force. I'm not really sure if you'd say that actually. I think you would just have to break it up and leave them separate because I'm not sure that there's really a clear way to combine these. Does it make any sense to add the forces? What does that even mean? Maybe if you can add the forces together, then call that some net force, then that net force would be 1, 2, 3, 4, 5, all 5 of these component forces added together. And then of course if you had a situation where, again, I don't know, I'm not sure yet off the top of my head if this works, but let's say that you had this object and for whatever reason it feels a force pushing it in this direction. And let's say that in this case the force, oh yeah, okay, so let's say that you were to add these together. If you had a graph, if you represented the data graphically, at this first point we see that force is m times g. Well, if one of these represents m, let's say this axis represents m, and this axis represents acceleration, which is not always g. Sometimes it is, sometimes it isn't. In the first part, so m is constant. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If we have these 5, each one of these tick marks represents m. So from here to here is m, from here to here is m, from here to here is m, and so on. But then we say, first we start off with the acceleration equal to g, which I'll put up here. You see that the force is equal to mass times acceleration. So the force is actually equal to the area of this shape. Now for the next one, we say that g is less than, or acceleration is less than g. I'll put it right here. But still, force is equal to mass times acceleration. Now, for this next set of jello or whatever, what would be this empty space here, we're back to normal atmosphere. And now, on the next part, let's say that the acceleration, so let's see if viscosity, so this one I think you would say is more viscous. I think it's resistance to flow, and this one's less viscous, unless I have that backwards. If what I said is true, then maybe it's going to be right here. It's going to be in between the acceleration through the first tub. It will be the acceleration through the first tub is slower than the acceleration through the second tub. So that's what this rectangle represents. And then the last rectangle is going to be the same as the first one. So in this case, to say the net force would mean to add up all of these, the areas of all of these individual rectangles. 1, 2, 3, 4, 5, of these 5 rectangles. Well, if we imagine a, let's see, if we imagine that gravity changes, or maybe it's not gravity, it doesn't really matter, but what the acceleration changes, maybe it's more proper to imagine the force changing, but if the force is what we're trying to find, then we should actually think about the force divided by the mass equals acceleration. But it's easier than mathematically to think of this as the force equals mass times acceleration. So we'll just go with this one, even though conceptually this one would be more accurate. Alright, so let's say that we have force equals mass times acceleration. So this ball right here is feeling some force that's pushing it in the direction of this arrow. But over time, let's say that the acceleration of the ball is changing, then if the change is constant, unlike here in this example where the change was just kind of, in chunks and random, but if it's constant and fluid, so that, well, I don't know if it has to be fluid. See, I think it's going to be accurate to say if it's differentiable, but yeah. So let's say that if the change is fluid, right? I'll just say that for right now. Maybe that's not the most accurate, but then we could end up representing by, let's say that when we graph it, we actually come up with this is acceleration, this is mass, and the acceleration is changing, but it's changing constant. So at first the acceleration is close to 0, and then let's say it grows exponentially. So in this case, force equals ma technically, but it would also be the area under this curve, because the total net force as the object moves through this thing I imagined. So let me redraw this because I took up my space. So we have this ball, and it's moving in this direction, and it moves through some crazy warpy thing that causes the acceleration to change over time. When it hits its stopping point, during this course of time, we have a net force. I think that's fair to call that a net force. It's the same thing I called a net force right here, so I'm going to use that word. So this net force would be actually the area under this curve here, which is still technically force equals mass times acceleration, but this would only be telling you the force at each little point. Maybe I should say at each little point here. I think I made the mass changing. Yeah, no, let's say, so the mass is not changing. So maybe you would say at each point here, because the acceleration is what's changing. I'm not sure which one's better, but anyway, you get the idea. So another thing that's done, which I haven't done yet, so I can't explain it like perfectly, but conceptually, I've done the mathematics already, so the concept is more or less clear. Basic idea. So let's say that we Alright. Yeah, so another example. Whoops. Let's get rid of that. Where there's constant change would be so there's constant change to acceleration, I guess would be a better way to say it. So if you had like this represents some ground, and maybe you had like a rocket like this. Gonna be a real simple looking rocket. That doesn't really look like a rocket. So you have this rocket, and so the rocket has fuel. Let's make this look a little better. There, it's a rocket. The rocket has fuel in it, right? So the mass of the rocket equals, so say equals, the mass of the rocket is not constant. Because I think a lot of a rocket's weight is from its fuel. So if the rocket starts to launch, then you know, it's gonna have some fire shooting out the bottom. I don't know, that's how I imagine it. I don't know a lot about rockets. So it has some fire shooting out the bottom, right? Well, it's doing that by burning up fuel. So it's gonna have this reservoir somewhere inside here that's filled up with fuel. And as this moves upward, it burns up fuel until at some point the reservoir is empty and there's no fuel. So we see that at the initial point we have M initial, the final point we have M final. So if you wanted to find, like say you wanted to find the net force, I don't know if that's going to be right to say that. At any rate, you can't fully say. So like force net does not necessarily equal mass times acceleration. Oops, I didn't make that a vector, so let's not make this a vector. And that's just because the mass changes. So maybe you could say the net force equals the sum of the masses times the acceleration. Maybe that's a fair way to say it. But at any rate, you have to do something mathematically to account for the fact that the fuel does not remain constant over the flight of the rocket, so that the mass changes drastically enough that it would have to be considered for whatever kind of a calculation you might be doing. Obviously, many things are ignored when doing calculations, but if something is going to make an impact on your final result, then it needs to be considered. And in this case, since the fuel comprises a good portion of the weight of the rocket, then you would need to take that into consideration when calculating. Maybe you want to know the acceleration of the rocket at any point. The acceleration is going to be changing over time because the mass is changing over time. And we see that acceleration equals force divided by mass. So hopefully that's clear enough.